What is going on, guys? My name is Amos and welcome to yet another video. So in this video we're going to be talking about the intersection of sets. So we use the symbol A and B. Now this is not an N, I like to call it a fancy N. Alright, so A intersection B is going to be defined as the set. So it's going to be defined as the set of all elements X in the set E such that X is in A and X is in B. Now, one more time, pay attention to the logical connector that is used. So basically here we have a conjunction. When we were talking about unions in the previous video, we had a disjunction, we had an or here. So here we have an and here. So for an element X, so A and B are subsets of the set E. So this is like your E is your universal set, and you have your A and you have your B. All right. So if X is in the set A intersection B, well then X has to be in the set A, and X also has to be in the set B. That is one thing that is important to remember. So if I have the set 1, 2, and 3, and I have the set B as the singleton set with 3, well then A intersection B is going to be the set that is going to only have 3, is the singleton 3, because we have that 3 is in both sets A and B, just like the way a conjunction is going to work. So we have this. All right, we have that. So that is your example. So what are some of the most important points that you guys are supposed to remember? Well, the first point is that A intersection B is always going to be a subset of A. Now this is easy to see, and that A intersection B is also going to be a subset of the set B, because we are extracting from the individual sets A and B elements that they have in common. So we are actually limiting the number of elements. So we are neglecting the elements that A and B don't have in common. So it makes sense that the set A intersection B is actually going to contain all the elements that will be in the set A intersection B are going to be in the set A, but A might have other elements. So A intersection B is always going to be a subset of A, and A intersection B is also going to be a subset of the set B. Now that is great. Now the second property that we are going to have is that A intersection the empty set is going to be, not equivalent. This is going to be A intersection the empty set is actually going to be the empty set. Well, because the empty set has no elements, it has no members. So A and the empty set have no elements in common. So A intersection B has to be the empty set. And whenever the intersection of any two sets is the empty set, we say that the two sets are disjoint. So the sets A and the empty set are disjoint because they don't have any elements in common. Whenever the intersection of any two sets is the empty set, then the two sets are going to be disjoint. Then A intersection A is A. Now this is easy to remember because this is evident. And A intersection A, not that. So A intersection E is the set A. Now remember, E is the universal set. It contains the set A. It also contains the set what? The set B. So the intersection of the set A and E is going to be the set A, because the elements that A and E have in common are the elements of the set E. are the elements of the set A. So A intersection E is actually going to be A. All right. Now the third property that we're going to look at is going to be that of associativity and commutativity. Just like the union of sets, the intersection of sets is also commutative. So A intersection B is going to be equal to B intersection A. And if you have any three sets, all right, we're going to have the property of associativity. It doesn't matter the order you follow when you're trying to compose them with respect to the intersection sign. All right. Now, that is great. And the last property is distributivity. So this is commutativity. Remember, whenever you can switch positions, you're talking about commutativity. Whenever the order in which you compose any two given elements with respect to a certain sign does not matter, you're talking about associativity. You're talking about associativity. Now, the last property that we're going to talk about is distributivity. Since we've talked about the union, we've talked about the intersection, let's now talk about distributivity. Like we are going to see that the union is going to be distributive with respect to the to the intersection, and the intersection is going to be distributive with respect to the what? To the union. All right. So that is what is going to be talked about, distributivity. We also had distributivity in chapter 1 when we discussed conjunctions and disjunctions. So this is actually a consequence of that discussion. This is a direct consequence of that important result. So let's talk about distributivity. So whenever you talk about associativity and commutativity, worry about the third property. Do we have the property, the distributivity property? And if we use that is what we also try to check. So this is how the things are lined up. So whenever you talk about associativity and commutativity, try to find out if you also have the the distributivity there. So A intersection B union C. All right. Well, the intersection is actually going to be distributive with respect to the what? With respect to the union sign. So we'll have A intersection B union A intersection C. Now that is great. And we also have A union B intersection C. So here what I'm trying to show you is that the union is also distributive with respect to the intersection. So basically we'll have A union B intersection A union C. That is all for this video. I'll see you in the next one.